Segway. The commercially available personal transportation system are simply two-wheeled robots. Two-wheeled robots, being inherently unstable, requires various rigorous control schemes to be applied to keep itself upright. These types of robots have gained a lot of attention in the field of research due to its versatility of operation. The objective of our project is to design a two-wheeled robot that can follow a predetermined path in its upright position even when disturbed. The robot must also stop its motion when the obstacle is detected in front of it. The Terasic's self-balancing robot kit is the platform we have chosen for the project. It contains all the sensors for achieving its objective except the IR sensor array, which helps it to detect the line. The kit is equipped with a DE10 nano board, a motor driver board, and 2 gear DC motors. The robot has to control the speed and direction of the motors based on the inputs from the available sensors to meet its objective. The DE10 nano board is the heart of the system with Cyclone 5 SoC containing an FPGA. The hardware drivers for the onboard sensors and interfaces are realized on the FPGA fabric using Verilog hardware description language. A NIOS II soft processor is also integrated on the FPGA to run the control algorithms. The motor driver board interfaces the ultrasonic sensor MPU6500 and the motor driver IC. The motor driver board is the backbone of the system. It contains an IMU for tilt measurement, ultrasonic sensor for the distance measurement between robot and the obstacle, motor driver IC to control the speed of the motors. There are 2 Hall effect sensors on the motors to measure its speed and direction of rotation. For the line following function, the IR sensor array is directly interfaced to DE10 nano through the GPIO pins. The hardware drivers for the sensors and motor controller are written in Verilog using Quartus Prime software and integrated with NIOS II soft processor using Platform Designer. This project file, when synthesized, generates an SOPC info file which describes the hardware layout and connections on the FPGA. The control algorithm, on the other hand, is written in C++ on NIOS II using the Eclipse software. The control inputs, which is already available to NIOS II processor, is used by the C program to enable the control. The balance controller, which keeps the robot upright, uses the input from MPU6500 and motor encoder by using linear quadratic regulator controller. The line following function, on the other hand, measures the deviation from the line using the input from IR sensor array and applies to a proportional integral derivative controller. The distance measured from ultrasonic sensor is used to decide if there is any obstacle in front of the robot. The controller parameters are meticulously chosen to improve the performance of the robot. The control signals generated by these controllers are translated to the pulse width modulated signal and is applied to the motor driver circuit. The binary files generated by the Quartus Prime and Eclipse are programmed onto the robot using a USB blaster. Due to the time limitation of these binaries, DE10 nano cannot be flashed permanently. Once the programming is complete, the robot is ready to perform its tasks. When the number 2 button is pressed on the remote control, the robot starts following the line and stops when the obstacle is detected. It resumes its motion only after the obstacle is removed. The robustness of LQR or balance controller is evident from the unflustered motion of the robot even when it is negotiating a sharp curve. Now let us see the robot in action.